The following diagram illustrates a vector-valued function defined by r of t is equal to sine of t cosine of t. The function assigns to each input value t a specific point in the plane. Unlike scalar functions, which return a single number, a vector-valued function returns a pair of values, one for the x-coordinate and the other for the y-coordinate. Together, these form a position vector originating from the origin and terminating at the point sine t cosine t. The result is a continuous motion along a circular path, as the sine and cosine values vary with t. This produces, in this case, a trajectory on the unit circle, with each point on the path corresponding to a different moment in time. In the diagram, the red point marks the current position, and the red arrow represents the vector from the origin to that point. Without much difficulty, we can extend the concept of vector-valued functions into 3 dimensions. In this example, the function is defined as r of t is equal to t sine of t cosine of t. Here, each value of t produces a vector with 3 components, one for each spatial direction. The x component increases linearly with t, while the y and z components oscillate sinusoidally. As a result, the curve wraps around the x-axis in a helical shape, progressing forward as t increases. This is a straightforward generalization of what we saw in 2 dimensions. Instead of tracing a circle, the output of the function now describes a smooth, continuous curve in 3-dimensional space. This kind of representation is commonly used to model the motion of objects through space, where all 3 spatial coordinates change over time. So how can this concept be applied in the real world? One practical example is in modeling the flight paths of drones. A drone's position in space changes continuously over time. To control or simulate its motion, we need a way to describe its trajectory precisely. A vector-valued function does exactly that. By assigning a time variable t to a position vector x of t, y of t, z of t, we can represent the drone's location at any moment. Let's consider how vector-valued functions help us analyze potential interactions between multiple drones in flight. This diagram shows 2 distinct flight paths, each defined by a vector-valued function r1 of t is equal to t minus 1 plus t, 5 minus 3t, and r2 of s is equal to 1 plus 2s, s, and 2. Each of these expressions describes a position in 3-dimensional space over time. The first drone moves along the red trajectory, while the second follows the blue one. Using this representation, we're able to determine exactly where and when their paths intersect. Without graphing, we can determine where these paths intersect using the component equations of the vector functions. Given r1 of t and r2 of s, the goal is to find values of t and s for which the position vectors are equal. That means the x, y, and z components must all match. Set the corresponding components equal. Starting with the third equation, since it contains only t, we get that t equals to 1. Now substitute t equals to 1 into the second equation. We get that s is equal to 0. If we substitute s and t back into r1 of s and r1 of t, we yield the same position vector 1, 0, 2. Here, we have 2 more vector-valued functions describing separate flight paths. r1 of t is equal to t, 1, and 0, while r2 of s is equal to 0, s, and 1 plus s. However, these 2 flight paths do not intersect. They're an example of what's called skew lines in 3-dimensional space. Skew lines are not parallel, but they also never cross. They exist in different planes, so no matter how far you extend them, they won't meet. In this case, the red path moves along a line that stays fixed at y equals to 1 and z equals to 0, moving only in the x direction. The blue path moves diagonally through the yz plane, with x equal to 0 the entire time. To confirm that two paths don't intersect, we can set their vector components equal and attempt to solve the resulting system for parameters t and s. From the third equation, we get s equals to -1. But the second equation says that s equals to +1. This is a contradiction. Therefore, the system has no solution, so the paths do not intersect. In such cases, it may be useful to calculate the minimum distance between these two lines. We can compute this with the following expression, where w is the vector connecting any point on line 1 to any point on line 2. v1 and v2 are the direction vectors of the two lines. v1 cross v2 gives a vector that's perpendicular to both lines. The numerator is the scalar projection of w onto that perpendicular vector, and the denominator gives the magnitude of that perpendicular vector, which normalizes the result. Let's try this with the previous example, where we showed that the two lines are skew. We define the vector-valued functions r1 of t and r2 of s. From these, we extract direction vectors v1 and v2, the point on each line p1 and p2, and the vector connecting the 2 points, w, which is p2 minus p1. Now compute the cross product. v1 cross v2 gives us 0, -1, and 1. Then compute the scalar projection of w onto this vector. w dot product v1 cross v2 gives us 2. And the magnitude of the cross product, the magnitude of v1 cross v2, gives us square root of 2. So the distance, d, is equal to 2 over the square root of 2, which is root 2. This tells us that although the flight paths never intersect, the shortest distance between them is root 2 units. This is the point-to-point separation along the direction perpendicular to both paths. In a flight planning scenario, this would be the minimum clearance maintained between the two drones. And that will be all from my end. Thank you for watching this presentation.